Hello, welcome to the Machine Learning at Home. Machine learning is a part of the great science of data analysis. And in data analysis, what is most important? Well, many people say p-value. P-value which somehow designate the significance of differences. P-values unfortunately are used too much. Not because p-value is a wrong thing, it's a very good thing. But it's very easy to use p-value in a wrong way and to interpret in a bad way, and also, which is worst, to somehow falsify it. So many effect size measurements were invented to replace or to somehow add to p-value. And if you want to work with data analysis, you should know some effect measure size. So effect size is kind of number which shows you difference between two or more groups. There are many ways to measure that difference. Some ways are better, some ways are worse. And I would like to present you with some, I think, better way. So let us run one library in R. So library SMD. So SMD stands for standardized mean difference. If you do not have this package installed, you should install it first with install.packages and smd in quotes, and then run library in parentheses smd. So how to use it? We need two or more groups to measure difference between them. So again, my beloved iris data would work very well for us. So first of all, we need to say smd. Actually, the package contains only one command, smd. And we, for example, want to measure differences between width of petal between three species of irises. SMD allow you to measure differences not only by two, but by many groups, which is, by the way, very good. So iris, petal width, not length. And we need to designate groups somehow. So groups are coded in a last fifth column, which name is iris species. That's it. So we can run it now, and you will see this is estimate of standardized mean difference between one species, which is not designated, it is Setosa, and two other species. What is good, you already see that mean difference, standardized mean difference, has a sign, in that case minus, so you can measure direction of difference. It's not always possible. And you can measure, as I said, difference between one species, which is first in list, so Setosa, versicolor virginica, Setosa is first, and any number of others. But I would like to show you some other interesting things from SMD. So SMD, for example, can measure the standard error. So we need only to add Std error equal to true in the end. So what is Std standard error? This is thing which show you how robust is your estimate. So in that case, for example, it's very good to know that standard error will not make the estimate equal to 0, because it's much less than extent of estimate. So if we, for example, will summarize -6 and 0.5 in both ways, so plus or minus 0.5, we do not reach 0, which is good. So estimate is not 0 at all, it's much deeper. Actually, authors of SMD and original paper says that SMD, well, equal at least to 1 is enough to show you that differences between groups is like a half overlap. So -6 is very big difference. And standardized error or standard error is sometimes not very good way to show you the actual, well, kind of interchangeability of your estimate. So people prefer confidence interval. So confidence interval is interval within which, with some probability, will lay your estimate. For example, we can make 95% confidence interval, and 95% confidence interval is, well, show you that estimate with 95% of probability will be between two values. So how to make it here? We need some manual work, but little bit. So first of all, we need to repeat previous command and write down in some new thing. So for example, iris SMD will be that new thing, and we will write results in it. Iris SMD is a simple data frame, which is very good. So now we need to calculate the lower confidence interval and upper confidence interval of 95%. So it's again very easy. So iris SMD, and we introduce new column in that data frame, low. So in that column we'll calculate from original data. So I use with command iris SMD, and we need simply to make very simple calculation. So estimate minus 1.96 multiplied by Std error. That's it, and it will be lower part of confidence interval. And then we can make a higher, so high, and we should change minus into plus. And now if you look on iris SMD, we will see these confidence intervals. So as you see, in versicolor, difference from setosa to versicolor can vary with 95% of probability from minus 791 to minus 585. And difference between setosa, which is not mentioned because it's first species, and virginica will vary from minus 9.9 to minus 7.3. So this is how to calculate confidence interval of 95% if you want. And the last very useful thing of standardized mean difference is that it can be applied even to factors, not only to numbers. So in that case, I will create factor artificially, like random. So let me calculate it. Factor of sample from letters 1 to 3. It's simply ABC, but letters 1 to 3 is kind of more elegant way to say the same. And the size of iris data, I know it very well, is 150. And we need to say also replace, because it's only 3 letters and we need to repeat them 150 times. So replace equal to true. And then 2 parentheses, right? And we should write it down in some object, for example, pp. Okay, so pp is, as you see, just letters, many randomly placed letters. So that will be our factor variable. And now we can calculate SMD. For example, with standard error, if you like, between pp and iris species. Okay, so now you see the differences in that random pp between setosa and versicolor is actually very low, and standard error will go to 0. You can easily calculate it. So confidence interval lays around 0, and this means that, well, there is no difference between species and that new artificial pp variable. But you understand the principle. So you can apply SMD to actually factor variable. So SMD, as you see, has many good things. I don't want you to replace it, replace p-value with SMD, but you can use it. And SMD is even recommended to use in clinical practice, which is very important, because in medicine we need to follow very strictly every statistical rules to avoid any possible mistakes. So SMD is a nice way to calculate effect size or in simple words, differences between multiple different things. So this is a kind of multivariate effect size, and which make it suitable for machine learning as well. Thank you very much.